Okay, so JFET function, field effect transistor is a type of FET that operate with a reverse bias. Okay. PN junction. Okay. To control the current in a channel, depending on their structure, they fall into either two categories, N channel or P channel. This is a symbol for N channel, and this one for P channel. Same thing you can see. This is the gate, the drain, and the source. Okay? The difference is for the N channel, the arrow coming in, and for the P channel, arrow coming out. That is the one you can either recognize N channel or P channel. Okay, in here you can see DC bias, VDD, provide the drain to the source voltage and supply the current from the drain to the source. Okay, this is a VDD. They will be supplied the voltage, okay, and the current from the drain to the source. Okay, VGG. Okay, set the reverse bias voltage between the gate and the source. In the past, you already learned bipolar transistor. This is NPN. This is the base collector emitter. From the base to emitter, basically that will be a diode. You can see diode. If VB greater than or equal 0.7 volt, diode will be on. So that will be turned on, the transistor. Okay? However, in the JFET, between the gate and the source, you get a diode, same thing. However, they opposite. Okay? So, that will be telling you if VGG or VG more negative, then diode will be on. Okay? This is the two sample showing you basically whatever they talk. I can telling you this is the drain, this is the source, and this is the gate. You get a negative VGG voltage. They connect the meter to measure the VGG, and also a meter connect to get the current ID. Okay? So on this picture here, you get maximum VGG or VGate, okay? Then you get the current ID. So that will be telling you one thing. This is the drain and this is the gate. Basically, this is a channel. If a channel wider, that more current flow. If they narrow, less current. And same thing for this picture. You can see they reduce the VGG, okay, less negative. And when you're looking into the current ID will be more, okay? And from the drain to the gate, this is a channel for the electron moving. If channel wider, more current flow, okay? So this also shows you the JFET when you're working on the level. Later make a little bigger picture. You see VGG or VGate, less negative. And that will be telling you current ID will be more and more bigger. If you're looking in your channel here, channel between the drain and the source, wider, that's why more current flow, and that's why you get more current. Okay, for this picture here, they try to display the current ID. This stands for ID, and this stands for VDF. Okay, you can see on the picture here, current ID keep going up to the point B right here. And if you're looking down, that will be VP, pin off voltage. And on the left, you can get the current ID. You call it IDFF. At the point B, current will be constant. Keep constant up to the point when you get a more current or VDD. That will be, you get up to the point, there will be a breakdown. Okay? So basically, they show you the home picture from 0 ID up to VPP here. This region they call a ohmic area. That means they can using add a resistance. Okay? From VP up to this point, the current ID, no change. They will be equal IDFF. Okay? When more current or when VDD higher, they go to the breakdown region. Okay? Now, the maximum drain current out of the FET occurs when the gate to the source voltage is 0. Okay, that means VGS equals 0. Then you can get maximum current ID. That means ID at S. Okay, if the drain voltage is too large, the JFET breakdown. Okay, JFET acts like current source when it is operating along the almost horizontal part of the drain curve. That means between minimum of VP and the maximum of VDS. The minimum voltage of VP equal a pin-off voltage. The maximum voltage VDS max equal a breakdown voltage. Between pin-off and breakdown, JFET acts like current source with the value of IDSS. IDSS stands for current from the drain to the source with shorted gate, means VGS equals 0. And the ohmic region, almost vertical part of the drain curve, equal a ohmic region that equivalent to the saturation region in the bipolar transistor. Okay, cutoff voltage, the value of VGS that makes ID approximately 0 is the cutoff voltage VGS off. The JFET must be operate between VGS equal 0 and VGS off. Comparison of a pin off and cut off. VP is the value of VDS at which the drain current becomes constant and is always measured at VGS equals 0. VGS off and VP are always equal in magnitude but opposite in size. Data sheet usually given either VGS off or VP, but not both. Now, if you look over again for family drain characteristic, this is the ID, this is VDS, okay, and this is the ID here, and this is a stand for VGS, negative 4, negative 3, okay, and at this point, ID equal IDSS, then VGS equal 0, right here, okay, so that's telling you if ID equal IDSS, VGS will be equal 0, okay. For this point here, if you know if you want to get the VGS, you go here, minus 1 volt. If you want the ID, you go left side, that will be ID, okay. Pin off when VGS equal minus 1 volt. Okay, VP, that means the voltage at that point, ID equal IDSS. Okay. Now, the JFET cut-off voltage. When you try to increase maximum for cut-off VGS voltage, and you looking in here, okay, channel open, no current flow, so that's why you get a 0 ampere, okay. At cut-off voltage, this is VGS off, VGS equal VGS off, and ID equal 0. Now, the basic operation of P-channel is the same as N channel device, except that P-channel requires a negative VDD and a positive VGS. So basically, both N channel or P channel, they work in the same way. However, the difference is VDD will be negative and VGS will be positive. That's opposite to N channel. Now, example. For the JFET circuit shown, given VGS off equal minus 4 volt and IDSS equal 12 milliamps. They want to know minimum value of VDD required to put the device in the constant current area operation. Now see what happened. Since VGS equal minus 4 volt, then you know VP equal 4 volt. At the beginning, we're already telling you VP or VGS get the same value. Okay? However, if VGS off, negative VP have to be positive. Okay? The minimum value of VDF for JFET to be in its constant current area. That means VDF equal VP. Okay? In the constant current area with VGS equal 0, ID equal IDSS equal 12 milliamps. The drop across the drain resistor RD, okay, here, RD, VRD, ID times RD, 12 times 560 ohm. You get 6.72 volt. Apply the chop law around the drain circuit. VDD equal VDS this is the D. This is the F. This is VG. Okay? VDD equal VDS. That means the voltage here. Plus VRD. That means the voltage drop here. RD. Adding the voltage VDS. You get 4 volts. Plus, okay, VRD. Okay, you get 10.7 volts. Okay, again, try to see what they're telling you. The minimum voltage value, VDD, required to put the device in the constant current area operation. Okay, so basically, they want to know what VDD is here. Okay, VDD, if you see, basically they equal the voltage drop across RD, adding to VDS, okay, and that's what we already calculated. The next one, JFET transfer characteristic curve for N channel. Okay, first thing, ID equals 0. Okay, when VGS equals VGS off, at this finger here. That is a VGS off. If you want ID, you go to the right, and ID 0. Okay, and also ID equal here, IDSS. Okay, when VGS equal 0. That means at this point here, if you want to get a VGS, you go in down, they equal 0. They get 2 points, so they get a curve here. Okay, that is a transfer characteristic curve. Now, example. When VGS equal minus 2 volts, VGS here equal minus 2 volts. Okay, basically, if you want to know the ID, you can see the line here. Keep going. And they hit the curve at the point 4.32 milliamp. Okay? Then ID equal 4.32. So that will be given to you the formula. This is the formula to calculate the ID. Okay? ID equal IDSS times 1 minus VGS over VGS of square. Okay? Next example. The Pakson data sheet of the JFET, okay, given IDSS 9 milliamp and VGS of equal minus 8 volts. Using this value, they determine the drain current ID. First, for VGS equal 0. Okay? If you can see VGS equal 0, that means the current ID equal IDSS. That's what they're telling you. Okay? A, VGS equal 0, ID equal IDSS. Second thing, VGS equal 1 volt. Minus 1 volt. Okay? For VGS equal minus 1 volt, you have to using this equation. Okay? To calculate ID. First thing equal IDSS 9 millivolt, milliampere right here, time 1 minus 1 volt divide VGS off right here, 8 volt. Okay, minus 8 volt. After calculation, this is the answer. Okay? Okay, next, for the JFET DC bias continuing. Okay? The forward transfer conductance, GM. GM is the change in the drain current for given change in VGS. GM basically, by the definition, equal delta ID divide delta VGS. The unit of GM, Simon. Okay? Data sheet normally given the value of GM at VGS equal 0 is GM 0. The GM can be calculated by the following. This is the formula following to calculate the GM. Okay? Transfer conductance equal GM 0 times 1 minus VGS over VGS off. And also, you need to calculate the GM 0. GM 0 equal 2 times IDSS divide to absolute value with VGS off. That means GM 0 cannot be negative anywhere. But normally, they can give data sheet given to you, GM 0. Okay? And basically, GM, that's what the transfer conductance GM. Okay? Example. The following information is included on the data sheet. For JFET, typically IDSS and VGS off. That's what they're given to you. And ym0. Using this value, determine forward transfer conductance Gm for VGS equal -4. Okay, so if you want to calculate the Gm, and that apply this formula. Okay, so Gm equal Gm0. That's what here. Time 1 minus VGS. Okay, divide VGS off. VGS equal 4 volt. VGS off equal -6 volt. Okay, so that you can get the answer here. And the value of ID at this point. Okay, you know the formula to calculate the ID. ID equal ID at S times 1 minus VGS divide VGS off. We already know. Okay, VGS is 4 volt. VGS off is -6 volt. Okay, and also another example. Okay, try to calculate the input resistance, input impedance or resistance equal VGS divide IGSS, absolute value. They given IGSS -2M, VGS equal 20 volt. You get the answer 10,000 mega ohm. Okay, JFET DC bias. Many techniques can be used to bias JFET. Okay. In our case, the gate source junction is reverse bias. The most common bias technique. First one, fixed bias. Second one, cell bias. Next one, voltage divider bias. That's almost the same bipolar transistor. Okay. Now, using the DC bias, you have to use either fixed bias or cell bias or the voltage divider. That means you need to calculate the voltage, the current, everything, DC. Now, you see, first on that one, so example, gate bias. Okay, that means, you know, this is the gate. This is the drain, and this is the source. Okay? For the gate bias, they connect negative voltage. Minus VGG to the gate. The next one, you can say, now if later on when you working using JFET as an amplifier, adding input signal here, adding capacitor, okay? They justify exactly bipolar transistor. What the name of the capacitor? Okay, so that's just a DC blocking or AC coupling. What that means? They allow the AC signal get through, okay, the capacitor, okay, to the gate, okay. That's why they say right here, no AC signal. So basically, let's say if RG were off-mid, as so in C, in the A, B, C here, no AC signal would appear at the gate because VGG is ground for AC signal. You understand it when you try to working on AC, on off the DC voltage connect to the circuit must be routed. So this one here, they must be routed. Okay, so if you get the voltage here, okay, and that get the DC, they will be short to the ground, so you don't have any signal. One of the most common way to buy out a JFET is cell buyer. So cell buyer, the different from the first one, okay? First one will be fixed buyer. The second cell buyer. How do we recognize? Now, this is a cell buyer. You see in here, they routed, not a negative voltage. Okay? So, for this one, for cell buyer, basically, you need the graphic. Okay? That normally not applied for technician. If you keep moving to be engineering, that you will need the graphic be given out. Okay? However, not for technician. Okay? If you're looking into the picture here, they given you the circuitry. VG equals 0. The thing is, this round. Okay, IDSS minus 10. VGS off minus 4. Okay, IDSS equals 10 milliamp. Okay. Now, the next one, voltage divider buyer. This one you already know. When you're working for bipolar voltage divider, that means you can calculate VG here. VG equals VDD times R2 divide R1 plus R2. Okay? Since the gate source junction has extremely high resistance. The R1, R2 voltage divider is practical unloaded. Voltage divider bias is more stable than either gate or cell bias. This is the one normally they use, better than two other ones. However, for voltage divider also they need graphic. Okay? Again, technician, you don't have to working on graphic. If you understand, that's okay. That's fine. Okay? If you buy the textbook, normally they're not using graphic at all. Okay, now see what happened. Gate or fixed bias example. For the circuit so they want VGS Q, IDQ, VDF, VF, VD. Okay? Now, they given IDSS 5 milliamp, VGS of minus 4 volt. Okay? So if I'm looking into this circuitry, I know this will be a fixed bias. The thing is they apply 2 volt negative voltage. Okay? Now we see solution VGS, VGS, okay, right here. VGS equal minus 2 volt. Okay, minus 0 volt. The thing is, VGS VG minus VF. Okay, however, VS equal 0. Okay, so VGS equal VG minus VS, VG equal minus 2 volt. Okay, here, minus 2 volt, minus 0. So that's why you get minus 2 volt. Okay, the next one, they want to calculate the ID. Okay, let's see. ID equal IDSS times 1 minus VGS divide VGS off. Okay, basically they have to be square. I think so. Let's see. VGS, the formula. Here, ID equal IDSS times 1 minus VGS over VGS of square. Okay. you get 1.25 milliamp. The next, they want VF. Okay, VF, that means voltage here will be 0. And they want VD, that's a D here. Okay, that's the same bipolar. VD equal VDD. Okay, let's see. VDD minus voltage drop across RD. Okay, so VD equal VDD minus ID times RD given you 9.25 volt. Okay. Now this is talking about cell bias. The thing is, this is not a negative voltage, it's routed. So they already telling you for cell bias you need the graphic. That means they given you this one. Okay, to solve the problem. So even you will have to do, I still try to explain to you. Okay, so let's see. VGF equal VG minus VF equal 0. Minus VF. Okay. VF means ID times RF. One thing you must know all the time. ID will be equal IF. Okay? Either ID or IF the same. So if you want to calculate the VGF, okay, equal VG minus VF. However, VG equals 0 here. No VG. Okay? 0 minus VF. VF, that means the voltage here equal ID times RF. Okay? Need to find A and B to draw the load line. Okay? So basically, the curve here, if you want to know the value, okay, or get the point on this line, okay, then, for example, you get the point in here, that will be given to you what ID equal, what VGF equal, okay? So, first thing, you need the true point to draw the line in order to get the Q point, okay? to point A and B to draw the line. First thing, point A. Okay, you get this point. At this point, what ID equal? You want ID, you go to the left here, 0. Okay, and the next one, ID equal 0. Okay, point A, ID equal 0. What VGS is also equal 0. Okay. Second thing, you need the point B. This is the point B here. Set ID equal any value. Okay. ID have to be greater than 0. That means you can get any point here to get the current ID. Okay? That means ID here, they will be ID at F. Okay? Select ID equal 10 milliamp. Okay? Equal 10 milliamp. Okay? Let's see. Then VGS equal 10 times 4700 ohm. That means they telling you to try to get the current ID. Okay, and now select ID 10 milliamp. Okay, that means ID at that here 10 milliamp. Okay, so you select the ID. Okay, 10 milliamp. Select ID 10 milliamp, and you calculate the VGS equal minus 4.7. Okay, VGS is of minus 8, so you can get the point in here. Okay, minus 4.7. Okay, so you can get this point B, this point A. You draw the line, so they cut the curve at Q point here. Okay, that will be given to you the value of IQ or VQ. Okay, in here for JFET and the graphic shown for IDQ. That means they want the current ID. Okay, you go to the left, and that's why you can see in here 1, 2, 3, 4, 5 volts, 5 amp. VGSQ, you going down here. Okay, they will be equal minus, okay, 2.5 volt, okay. This is the 0, okay, to the left, negative, to the right, positive, okay. And you want to calculate the VD here. Okay, VD equal VDD time voltage drop across RD, ID, RD, okay, VDF, VD minus VF, okay, so summary of the cell bias, okay, to solving a cell bias, either they given you a little more information, write down the graphic. If you don't have any more information, then they have to give to you the graphic. That is the way. You have to draw two points, intersection between the line of that two points with the curve. You can find out what ID or what VGF. Okay, the last one will be voltage divider. Okay, this is the voltage divider. If you want to calculate the VB, that will be VB. Voltage divider, take VDD, time R2, divide R1 plus R2. Okay? Then you calculate 2.A. And B, to draw the load line. To get a point A, set ID equals 0. Okay? Then VGF, okay, you know that will be that right here. That is the rate. VGF, okay, to get an A, set ID equals 0. ID equals 0. Then VGF equal 4.84. That means they have to give you graphic here, okay, to solving for DC bias. So, what they telling you, okay, to get point A, in order to get point A, okay, this means point A here. Point A here, ID, let's see. To get an A, SVGS equal 4.8 volt and 0.3, 4.8 volt. Okay. Let's see. To get point A, set ID equal 0. VGS 4.8 minus ID times 3.3. Let's see. That I think will be a point B. Point A right here. Okay. At this point, ID equal 0. Okay. ID equal 0. Then VGS equal 4.8 ID. You can see the formula right here. VGS equal VG minus ID times RF. Okay. Sorry, that one. That's a VG. Okay. So VGS VG minus VF. Okay. And VG we already calculated voltage divider. VF means ID times RF. Okay. So ID equals 0. Okay. So VGS equals 4.8 volt minus ID times RF ID 0. So that's why you get 4.8. Okay. That means point A. That means point A right here. You get V you get let's see, VGS equals 4.8. Okay. Now you need the second point B here. At this point, VGS equals 0. And ID will be this point here. Let's see. To get point B, VGS equals 0. Then you using this formula. VGS equals, okay, 4.8 volt minus ID times 3.3K. Okay, so that one you calculated, let's see, they given to you ID equal 4.8 divided to 3.3, you get 1.45. Okay, that means this one 1.45. And now you get the line. They cut the curve at this point we call a Q point. And at Q here, you want ID, go to the right, go VGS, going down. Okay? And that's just an example to let you try to do. Okay? You can try that. Now, we want to emphasize here. If you're looking into the circuit, what type of DC bias? Cell bias, fixed bias, voltage divider bias. Then you have to recognize. If not, you cannot solve the problem. I'm looking here. No negative voltage here. So this will be a cell bias. Cell bias, they need the graphic to solve the problem. However, they say, do not cell bias, do cell bias without graphic. Now, if without graphic, they have to telling you what they telling you in here. They given to you ID equal 1 milliamp. Okay? So first thing, they want to calculate VG. Okay? You know, G is right here. Okay? That will be the drain. That will be the short. Okay? That the VG equal the current. Let's see. ID equal 1 milliamp. Also on the time equal IF. Okay? VG will be equal 0. Nothing here. So that's why. Okay? Now they want to calculate VF. VF means voltage at the source. VF equal. Okay. Let's see. 1 time 1K. That's why. You can get 1 volt. And they want to calculate VGS. VGS equal VG minus VF. VG 0. Okay, VF 1 volt. So 0 minus 1. Minus 1 volt. And they want VD. VD here. VDD. Minus ID times RD. And VDF equal VD minus VF. Okay, on this one, the same thing. Let's see. Graphically determine. Okay, if you want, you have to try to understand for voltage divider graphic here on this one. If you can understand that, then you will be able to working on that one. Okay? Let's see. Graphic determine IVGSQ, IDSQ. Okay. Easy to calculate that one voltage divider. VGS equal VG minus VS, where VS equal ID times RS. Too complicated. Therefore, we need graphic. Need 2 points to draw the line. Same thing, using graphic, and that's what we don't want to do it. And more solving on that problem. Okay? This is the one you will be doing. For voltage divider bias, you have to get graphic. Now, they say, I don't want graphic anymore. So that's why they given VD. Okay? VD equal 7 volt. If I want to calculate the ID, okay, equal IS equal VDD. Okay, minus VD divide RD. Okay, and they already given you 7 volt. Okay, so first thing they want VG voltage divider. Okay, and they want ID given. Okay, ID VDD minus VD. That means, okay, you get 12 minus 7 divide 3.3K. And VS, same, VS means IS times RS. VGF VG minus VF. You already get VG. You already get VF. And last VDF, VD, VF. You already get VD. And VF, you can calculate it. Okay? So basically, that will be completely done. Okay? So, we'll see you in the class. Okay? Bye-bye.